Okay, a slightly more complicated one. V in this time going through a resistor, and then the network to ground is a capacitor in series with a resistor. So we've got that. Again, the standard question would be work out where the poles and the zeros are and determine the shape of the Bode plot. Let's call that R1, that R2, and that C. This means that we could then write our frequency response, V out over V in. Once again, it's a potential divider. This time, the total impedance of this part of the circuit here is 1 over J omega C plus R2, using the complex impedance of the capacitor. And then the total impedance in the divider is R1 plus 1 over J omega C plus R2. Again, what we're trying to do is get a polynomial divided by a polynomial. We haven't got that because we've got terms in J omega underneath a 1 over thing here. So we'll multiply all of these 5 terms by J omega C. That should leave the ratio unchanged, and that will give me 1 plus J omega C R2 divided by 1 plus J omega C R1 plus R2. Comparing that to the standard form, 1 plus J omega divided by the 0 over 1 plus J omega divided by the pole, we can see here that the 0 is going to be at 1 over C R2 radians per second, and the pole is going to be at 1 over C R1 plus R2 radians per second. And again, if I wanted them in hertz, I would just take these and divide them by 2 pi. What does that look like on a Bode plot? Well, you can see that the pole here is going to be at a lower frequency than the 0. So I'm going to come across the pole first. At 0 hertz, where the Bode plot begins, this is gain here expressed in dBs. This is frequency. At 0 hertz, right down here, very low frequencies, that term is going to be negligible compared to 1. That term is negligible compared to 1. And again, we're just going to get 0 dBs. So we're starting here. We're going to carry on until, well, we're going to get to the pole first, because the pole is at a lower frequency. So we're going to bend down when we get to the pole. When we get to the 0 frequency, we're going to bend up by 20 dBs per division, per decade rather, which means we're now going to carry on horizontal again. That is the pole frequency, that is the 0 frequency, that is the Bode approximation. The actual shape of the real circuit would look something a bit more like that. Excuse my drawing. But it's the same technique. Have I got time in this video for the next one? Probably yes. Another first order circuit to try would be something like this one. Slightly more complicated perhaps. V in goes to a resistor, then there's a capacitor in series with a resistor and a resistor down to ground. V out. Call this one R1, this one R2, and this one C. Okay, this time we've got a parallel combination here. So using the standard formula for 2 components in parallel, the total impedance of this parallel pair, Z total, will be Z1 times Z2 over Z1 plus Z2, where Z1 is R1 and Z2 is 1 over J omega C. So here we have V out over V in is equal to, well, that's just R2 in this case, divided by the total impedance of the potential divider, which is R2 plus the impedance of this network here, which is these 2 components in parallel, which is R1 over J omega C, that's the Z1 times Z2 bit, divided by R1 plus 1 over J omega C, that's the Z1 plus Z2 bit. That gives us that. We want this as a polynomial, it's not a polynomial. It doesn't look anything like a polynomial, so we're going to have to do some algebra on this again. Once again, a good way to start is to multiply everything through by j omega c. That gives us R2 times j omega c divided by, down here, R2 times j omega c plus, and then this term here times j omega c, that would just be R1 divided by R1 plus 1 over j omega c. Right. Probably not the best way to do it, come to think of it, but we'll carry on. What I'll do now is multiply through by this term down here, R1 plus 1 over j omega c, and we've got three terms, this one, this one, this one. Multiply them all by R1 plus 1 over j omega c, and I would get R2 times j omega c times R1 plus 1 over j omega c divided by R2 j omega c times R1 plus 1 over j omega c plus R1. Multiply those out. That would give me R1 R2 j omega c plus, well, this times this, the j omega c's would cancel and I would just get R2. On the bottom we'd have the R1 there. This term times this term here would just be R2, and this term times this term would be R1 times R2 times j omega c. There's an easier way to do that, but as long as you get to the answer, that's fine. We're trying to get this into the general form of some gain, some low frequency gain, times 1 plus j omega over the frequency of the zero divided by 1 plus j omega divided by the frequency of the pole. And we can do that with a bit more algebra. Here we've got j omega c, R1 and R2, but we don't have a 1 here, we've got an R2. So we take the R2, common factor of R2 out of this, and that leaves us with R2, 1 plus j omega c, R1. Similar thing down here. We would like 1 plus something times j omega, but we've got R1 plus R2 plus something times j omega, so we take the factor of R1 plus R2 outside a bracket, and we'd end up with this. R1 plus R2, 1 plus j omega c, R1, R2 over R1 plus R2. And if I multiplied that out, I would just get back to this again. We've now got something in our standard form. The gain at low frequencies, R2 over R1 plus R2. There's a pole at this, due to this term here. The pole will be at R1 plus R2 over CR1 R2, and there'll be a 0 up here at 1 over CR1. And again, if we wanted to plot what that looks like on a Bode plot, we would end up with something like, well, we're not starting at 0 dB anymore. At very low frequencies, we would start off with a loss given by whatever R2 over R1 plus R2 is in dBs. We would then come across a pole, and here the pole is at a higher frequency than the 0, so the first thing we'd come across is the 0. We would bend up at 20 dBs per decade until we got to the pole frequency, that's the 0, the pole frequency here, at which point we bend down at 20 dBs per decade again, and carry on like that, in theory, for infinity. That's h of omega in dBs, and this is the log of the frequency, as usual for a Bode plot. Right, that's enough for first order ones. The other one you're likely to come across is a second order circuit, but we'll talk about that in the next video.